Hello, I'm Yoichi Sato from the University of Tokyo. It's my pleasure to have this opportunity to introduce our recent work on egocentric vision. Please forgive me for giving this presentation as a pre-recorded video because I cannot attend EPIC workshop in real time. Egocentric videos captured by a wearable camera allow us to observe our activities closely and continuously from the first-person perspective. That's why we are all interested in techniques for analyzing egocentric videos to understand various activities like hand-object interactions and human-to-human interactions. In this talk, I would like to talk about our recent work on several topics in egocentric vision: spatial segmentation of hand regions, temporal segmentation of actions, and gaze prediction from egocentric videos. Let me begin with hand segmentation. Hands are among the most commonly observed objects in first-person videos, and therefore, hand segmentation is essential for various objectives of first-person video analysis. For this reason, the problem of hand segmentation has been studied extensively, and we have seen significant performance improvement in recent years, especially with the use of CNN-based models. This video shows the accuracy level of the current state-of-the-art hand segmentation models. As we can see, hand regions are correctly found despite the complex background and significant camera motion. However, the performance of a hand segmentation model drops significantly when the model is applied to another dataset different from the ones used for training the model. This motivated us to develop a new approach for adapting a pre-trained hand segmentation model to an unseen environment without hand segmentation labels. This example shows how the performance of the hand segmentation model can improve after adaptation. So the goal of this work is to generalize hand segmentation across different environments. It can be viewed as a domain adaptation problem. That is to say, we would like to adapt a hand segmentation model pre-trained on a source domain to new target domains without using new hand segmentation labels, which are expensive to prepare. Previous work has shown that an FCN-based model could significantly improve hand segmentation performance in egocentric videos. However, it may fail in videos recorded in new environments with significantly different lighting conditions and backgrounds from those in the videos used for training the hand segmentation model. Recently, many unsupervised domain adaptation techniques were proposed to tackle the generalization problem. In particular, the idea of self-training based on pseudo-labels has been developed as a unified and efficient approach for domain adaptation. However, existing self-training methods mainly use softmax prediction scores to extract pseudo-labels, which may not reflect the model's real confidence in its prediction. As a result, the performance of generalization is limited. We investigated the relationship between force segmentation and softmax-based prediction score, and we found that the prediction score has no direct relation with the model's confidence or uncertainty about its prediction. For example, figure B shows the prediction score of hand region segmentation and grand choose hand regions. As we can see, only a part of the left hand region is correctly found. However, the uncertainty map obtained through the prediction score is overconfident with the misdetected right hand region, where lower brightness means less confident. Simply, this uncertainty map is unreliable. To adapt a model to a new environment, it is essential to know the model's uncertainty about the new environment. We found that existing approach on Bayesian CNN can provide an appropriate solution for uncertainty estimation as shown in Figure D. Bayesian CNN provides a useful tool for estimating uncertainty by modeling posterior probability conditioned on model parameters. In particular, we follow the work of Gao in ICML 2016 for efficient Bayesian inference with dropout. The model uncertainty can be estimated by multiple stochastic forward passes of a CNN with dropout enabled. Here is an overview of our method. Our method uses two critical components for training hand segmentation model. The first component is the use of model uncertainty maps estimated by Bayesian CNN as guidance for iterative self-training. Basically, the hand probability maps and uncertainty maps obtained by the segmentation model at the previous iteration are used for training the model at the next step. The second component is a pre-trained hand shape discriminator to enforce hand shape consistency across different egocentric videos. For more details of this method, please refer to our paper presented in the main conference of this CVPR. We use multiple egocentric video datasets shown here to evaluate the generalization performance of hand segmentation. EGTEA dataset, which contains 10,000 images with hand masks, is used as a source domain for training the segmentation model. Other datasets are used as target domains, in which the hand segmentation masks are only used for evaluation. This shows the performance comparison with the baseline hand segmentation model called RefineNet from CVPR 2018, and two other state-of-the-art domain adaptation methods for semantic segmentation. We used intersection over union as evaluation metrics. The result shows that our method shown in yellow achieved the best generalization performance. The more domain gap the dataset has with the source domain, the bigger performance improvement our method can achieve. This is most clearly seen in YHG dataset. On the other hand, we observed limited performance improvement with GTEA dataset and EgoHand dataset. This is because the image quality of GTEA dataset is the most similar to EGTEA dataset, and therefore the pre-trained RefineNet already performs well. Also, EgoHand's dataset contains a mixture of hands seen from both the first-person and second-person perspectives. Since our method is trained only for hands seen from the first-person perspective, the performance improvement on EgoHand's dataset is limited. This is a side-by-side comparison of hand segmentation result before and after model adaptation. This is another example. We can see that our model adaptation method improves the hand segmentation even in challenging cases where lighting and background change significantly. Here we show the change of uncertainty as well as segmentation result at different iterations on YHG dataset. we can see that with more iterations of self-training, the uncertainty of the model prediction gets smaller and the segmentation becomes better. Similar results can be seen with EDSHK dataset. Next, I would like to talk about action segmentation. Given an untrimmed video sequence, the task of action segmentation is to locate all action segments temporally and classify their categories. Some of the previous works use a sliding window-based approach with segmental models for action segmentation. They first slide a neural network with a fixed window size to extract clip-wise features, and then add a temporal model on top to capture the pairwise temporal relation between segments. Their model can reduce action over segmentation errors by limiting the maximum number of candidate segments. However, the sliding window-based approach tends to perform poorly when actions are relatively long. Another line of research uses recurrent models for action segmentation. Typically, they use a two-stream network to learn representation of short video chunks. These representations are then passed to a bidirectional LSTM to capture dependencies between different chunks. However, LSTMs only have a limited span of attention and tends to be very slow to compute. Recent state-of-the-art methods for action segmentation use temporal convolutional networks. Their approach follows an encoder-decoder architecture with temporal convolution and pooling in encoder, and upsampling followed by deconvolution in the decoder. In these TCNs, the stack of temporal convolutional filters enables the network to capture long-range patterns with a large receptive field. TCN-based action segmentation was firstly proposed by Lee et al. In CVPR2017. After that, other people extended TCN-based action segmentation by using different tricks such as deformable convolution, residual connection, and dilated convolution to improve receptive fields. Because increasing the range of a receptive field is crucial for enhancing action segmentation performance. Despite the success of the TCN-based action segmentation, we argue that there is a major limitation in the existing action segmentation methods, especially in dealing with egocentric videos. Let's see this egocentric video as an example. We can clearly see the actions of taking the bottle and pouring water in the glass. However, during this time, we cannot clearly see what action is taking place. Then finally, we can observe that this person puts the glass onto the table. As we saw in this video, some actions may not be observed clearly due to the limited field of view and large camera motion in egocentric videos. The existing action segmentation method would have difficulties in correctly finding such unseen actions in egocentric videos. On the other hand, we humans can easily understand what action takes place between pouring water into the glass and putting the glass back on the table, based on the relation between the two actions. In this case, we know the middle action is likely to be drinking water. Based on this observation, our idea in this work is to perform relation reasoning over action segments for better action segmentation. More concretely, we propose a graph-based temporal reasoning module on top of backbone segmentation networks to refine the segmentation. We use graph convolutional neural networks as a key tool to model the temporal relation and update the features. The input video is first processed by a backbone model to obtain hidden representation H and an initial segmentation result Y. In the GTRM, we map the representations into two graphs with different kinds of edges. The first graph, called RGCN, is used for segment boundary regression. The second graph, called CGCN, is used for segment classification. After using graph convolution to refine the node representations, we remap the nodes to a refined representation. We then use it together with the previous hidden representation to obtain the refined action segmentation y-hat. Here are the results of experiments on the EGTAI dataset. The first row shows the result of the two-stream network that is applied for each frame on the whole video. As we can see, the two-stream network performs poorly since no temporal dependency is considered. The previous works on action segmentation are listed in the middle. MGRU is a baseline that uses a multi-layer gated recurrent unit. In the bottom, we see that by adding our GTRM on the backbone model, we can achieve significant performance improvement. Next, I would like to show you one qualitative result on this video clip from EGTAI dataset. Here is a visualization of the action segmentation and classification result for video clip. In this example, please see the closing action near the end of the clip. The closing action is observed only briefly with rapid head motion. And as a result, the action is not detected with the baseline model. On the other hand, because of the preceding actions of opening the fridge and taking tomato, our method successfully detects and segments the closing action. Here are the results of the ablation study on GTAI dataset. We replace each of the GCNs within our module with a fully connected network that doesn't consider relations among nodes. We can see from the table that GCNs that consider the temporal relation of the segment can have a positive effect on action segmentation. We compare the performance gain by adding our GTRM module on three different datasets, EGTAI, 50 salads, and breakfast datasets. 50 salad datasets and breakfast datasets are the two main datasets used in action segmentation. But the videos in these datasets are significantly shorter than those in EGTAI dataset. Each video in EGTAI dataset contains about 160 actions on average. On the other hand, each video in 50 salads dataset and breakfast dataset contains about 20 actions and 5 actions respectively. As a result, the performance gain on these datasets is limited. That is because there are not so many action instances per video, so the relation reasoning doesn't work effectively here. Lastly, I would like to talk about the problem of egocentric gaze prediction. Our goal here is to predict gaze positions from first-person videos. This example shows a probability map of a gaze position in the current video frame. We believe knowing gaze positions can be useful for analyzing human activities from first-person videos. We are not the first to deal with the problem of gaze prediction from egocentric videos. People have already studied to use various cues that are unique to egocentric videos, in addition to video saliency, to predict gaze positions. Such cues include head motion and location and poses of both hands. People also started to use convolutional neural networks for better video saliency modeling. By properly training a network, we can leverage egocentric cues such as head motion and hands to achieve better prediction accuracy. Here I would like to emphasize one thing about the existing methods. They are all based on a bottom-up approach. For instance, given an input video, we can use an encoder-decoder style neural network to predict gaze positions. This is typical and direct bottom-up approach for gaze prediction. But it is well known that our eye movement heavily depends on a task we are carrying out. Even if we are looking at the same scene, our eye movement would be significantly different depending on what we are trying to do. This important aspect of our eye movement is not considered in the existing methods. Based on the observation, our idea here is to incorporate attention transition patterns that are associated with a specific undergoing task. For instance, when we take pizza out of the fridge, we first look at the fridge and then shift our attention to pizza. When we're cutting the sausage, we first look at the knife and then pay attention to the sausage. Such attention transition patterns are highly characteristic with the task of cooking in a kitchen. We want to leverage such information for improving gaze prediction accuracy from egocentric videos. This is an overview of our method. Given the current RGB image frame and stacked optical flows as input, we use the spatial CNN and temporal CNN to get deep features. These features are then passed to the saliency prediction module to get the gaze probability map in a bottom-up manner. The input features are also given to the attention transition module to get the gaze probability map based on a task-specific and semantic level attention transition patterns. In the attention transition module, the LSTM-based attention transition model generates a gaze probability map based on attention transition at object category level if the fixation state predictor says there is a saccadic eye movement. The attention transition module is pre-trained by using egocentric videos with eye tracking data for a specific task of focus. Finally, the outputs of the two modules are then fused to generate the final gaze probability map. For more details of our method, please refer to our paper published at ECCV2018. This slide shows one example of gaze prediction. The bottom right is the ground truth gaze positions measured by a mobile eye tracker. The top left shows the gaze probability map obtained by the saliency prediction module alone. The output of our full model is shown at the bottom left. Let's take a closer look at the attention transition predicted by our model. This is an example of the attention transition from pizza to plate. We can see from the top left video that the video saliency prediction module cannot predict attention transition in a bottom-up manner. On the other hand, our full model in the bottom left can successfully predict attention transition from the pizza to plate. This shows the result of comparison between our proposed method and other baselines on two benchmark datasets, GTEA Gaze Plus and GTEA Gaze, by using two standard evaluation metrics for gaze prediction, average angular error and AUC. The first two baselines are representative video saliency models, and in error and deep future gaze are two recent methods for gaze prediction using egocentric cues. As we can see in this table, our method achieves much better accuracy than all of the baseline method, with a more than 40% reduction of average angular error. In this talk, I introduce our recent works on three topics in egocentric vision: hand segmentation, action segmentation, and attention prediction. Before I conclude my talk, I would like to acknowledge my collaborators: Yifei Minji Sai, Fen Liu, Zhenchen Li, and Yusuke Sugano. Thank you very much for your kind attention.